Now on these next few, we have cube roots, which means we're looking for groups of 3 instead of groups of 2. We know that the first problem is not reduced because we have a radical still in the denominator. So because this can't reduce, I'm going to go on to step 2. Step 2 says to factor out the denominators under the radicand. So we have 2 times y. Well, that's factored completely. And step 3 says I need to multiply by any extra values so that I can make my denominator have only groups of 3. On the original denominator we have a 2. Well, in order for it to go out of the house, clearly I need to have 3 2's. So how many extra 2's do I need to multiply? I'm going to have to multiply by 2 more 2's. On the y, I have 1 y, and I need 3 copies of y. So because I want 3 copies of y, that means I need to multiply 2 more copies of y. Whatever you do to the denominator, you must also do to the numerator. So looking at the denominator again, this group of 3 gets to go out, the group of y gets to go out, and now I have no more radical in the denominator. That's exactly what I was hoping for. In the numerator, don't forget the little 3 on your cube, I have 5 times 2 times 2 times y, and these are all under the radical, so I put them all under the radical. Do I have any groups of 3 here? These are all prime factors and no groups of 3, which means all of them will stay under the radical. But I can multiply this to make it a little bit more simple. 5 times 2 is 10 times 2 is 20 y squared. And this is my final answer. Nothing more can reduce because the 2y is out of the radical, and on the numerator all of the values are inside the radical, so they can't talk or reduce whatsoever. On our next problem, it's not reduced because we still have a radical in the denominator. 5 and 9y don't reduce as is, so the next step is I would like to factor out the denominator. So 9 is 3 times 3 times y. That was step 2. Step 3 says I'm going to multiply the numerator and the denominator by some value in order to make my denominator only have groups of, in this case, 3. My original denominator had 2 copies of 3, but because I'm looking for perfect cubes, I need 3 copies of 3. Because I had 2 and I need 3, that means I need to multiply by 1 more extra in the red. With the y's, I have 1 y, so that means if I wanted to come out of the house entirely, I would need to have 3 y's there. So in order for it to have 3 y's, that means I need 2 extra y's under the red radical. Whatever I multiply the denominator, I also then have to multiply the numerator. Don't forget these are cube roots, so I'm leaving off my little cubes there. So looking at your denominator, we have a group of 3, and that comes out. Great. I have a group of y, and that comes out. And then I have to go back and finish up my numerator. So in my numerator, I have a 5. Since they're all under the radical, I can put them all together. It doesn't look like there is any groups of 3 here whatsoever, and they have to stay together. It is totally okay for you to have extra things under the radical in the numerator. The rule just says we're not allowed to have any radical things in the denominator. So we've done all this work just to make sure that the original problem doesn't have any radicals. Okay, on our last problem of this type, we can't reduce 2y over 9x to the 5th. So the next thing I'm going to do is to break up these into 2 radicals and factor the denominator, which is what step 2 tells us to do. So 9 is 3 times 3, and then x to the 5th, that's 5x's. Next, I'm going to multiply both the numerator and the denominator by some value, and I'm going to be a little bit sneaky about it because I want the denominator to have only groups of 3, because that's what my index is. So I have 2 3's to begin with. but now I need 3 3s, which means I need one extra copy of 3 so that I can have 3 3s and they can go out as a group. As far as x's, I have 5 x's, but 3 of them together would make a group. And I have 2 more, so I need a group of 3, so that would mean I would need 1 extra. So I'm going to multiply by 1 extra in red so that I have a perfect group of 3 down here. Don't forget, whatever you multiply to the denominator, you also then multiply to the numerator. That leaves me with 2y and 3 and x in the numerator. In the denominator, hopefully everything will come out. We were trying to make that happen. So the group of 3 comes out, a group of x comes out, and another group of x comes out. A short way of writing that, so I don't have to rewrite this, is just 3x squared. In the numerator, I have cube root, and 2y and 3 and x are all in the radicand. There is no copies of 3, so I am going to multiply all of the rest of the values, and that will be my final answer. Nothing else can reduce because the numerator is all under the radical, the denominator is all outside the radical, so there cannot be any reducing left. Our next topic is to add and subtract radicals. Now, when you add and subtract radicals, it is very similar to adding and subtracting variables. So, for example, 6x plus 3x is 9x. But when I ask you what is 6x plus 3y, notice the x and the y are not like variables, so you can't actually do anything with this. Okay? It just stays put. The 6x and the 3y are not like terms, so they can't add. But the 6x and the 3x are like terms, so they can add. Now, notice that the first problem added together because they had like terms. The second problem didn't add together because they didn't have like terms. Notice that in the first problem, the coefficients add together, so the 6 and the 3 added together to get 9, but the variable stayed the same. So similarly, when we add or subtract radicals, the radical parts have to be the same, or we can call those similar or like radicals to be able to add or subtract. So if I have 6 square roots of 5 plus 3 more square roots of 5, well, that just gets me 9 square roots of 5. Notice, just like in the variables, the x stayed the same, so does the radicals. The radical 5 has to be the same, and then it stayed the same. All we did was add the numerators. But when I ask you what's 6 square roots of 5 plus 3 square roots of 2, root 5 and root 2 are not the same things. So we can't actually reduce those at all. Notice that the first problem added together because they had like radicals. The second problem didn't add together because they didn't have like radicals. And notice that on the first problem, the coefficients added together, the 6 plus 3 gets 9, but the radicals stayed the same. So the steps for adding and subtracting radicals are: step 1, simplify all radicals. Step 2, rationalize any denominators if you need to. And then step 3, add the coefficients of all like or similar radicals. Don't forget to keep the radical part the same. So the radical part has to be the same in order for you to add them, and then once they are the same, you better keep it the same. So on the first problem, all of the radicals are already reduced. 2 is prime and can't break down anymore. There's no denominators to reduce. So step 3 says add all like radicals. So I'm going to add the coefficient part only. Root 2, root 2, root 2 are all like radicals. So I am going to keep that root 2 the same, and all I have to do now is add the coefficients. So 4 root 2's plus 3 root 2's is 7 root 2's. And now I'm going to do one more. The root 2 is the same, so it's going to stay the same, and then I just subtract my coefficients. Now you have to be a little bit careful here. That's like a coefficient of 1. I have 1 copy of root 2 here. 7 root 2's take away a root 2, or really 1 root 2, is 6 root 2. On the next problem, root 40, root 90, and root 160 are not all the same. But that's okay because step 1 says to simplify all of the radicals. So 40 is going to break down into 4 times 10, 2, 2, 2, and 5. So this 2 gets to go out. The 2 and the 5 stay inside the radical and multiply. But please, please, please don't forget that there's a minus here. So you have to bring down any outside coefficients or signs down into the problem after you reduce. On the next problem, we have 90. So 90 can break down into 9 times 10, 3, 3, 2, and 5. The 3 comes out. The 2 and the 5 stay home, so they multiply to 10. But again, we have a minus sign here. So don't forget to bring that minus sign down. And then on the last one, I'm just going to go ahead and bring that minus sign down right now. On the last one, I have root 160, which gets me to 16 times 10, which is 4 times 4 times 2 times 5. Now here's a shortcut I can show you. 4 clearly goes down to 2 and 2, and then 4 goes down to 2 and 2. But because I'm looking for groups of 2, because it's a square root, if you see groups of 2 of composite numbers that could possibly go down some more, it is okay if you don't break them down completely and just take the 4 out by itself. The 2 and the 5 stay home, and that gets you 10. Now, if you didn't want to do it that way, you could have kept going and done 4 and 4 and 2 and 2 and 2 and 2. But look, both 2's will come out of the house, they'll multiply, and you'll still get 4. So you did not need to break it all the way down. You could have stopped when you saw 4 and 4 and grouped it up. Either way is going to work. All right, now let's take a look at the like radicals. So it looks like the root 10, the root 10, and the root 10 are all like radicals. Yay! Which means my answer is going to stay root 10. All I need to do now is add or subtract the coefficients. So I had negative 2 root 10s. Then I took 3 of those away, so that gives me negative 5 root 10s. And then that's minus 4 more. That's negative 9 root 10s. So my final answer is negative 9 times the square root of 10.